Adnan is the CEO and founder of Brecker and noted as the father of portable stimulus. Having worked on his technology for 15 years, both at Brecker and A&D, he collaborated with many verification teams at leading semiconductor companies to perfect and adapt the approach to their actual needs. Brecker is one of the leading providers of portable stimulus-based verification and has engaged with many design teams globally.
Thank you. So welcome everyone. Thank you for having me here. And here I am in sunny Bristol, or not so sunny. Okay, how do I drive this thing? Are you going to fix the... Okay, good presentation, Tom. Really enjoyed that. So I'm here to talk to you about portable stimulus, about Brecker's particular journey, my particular journey through portable stimulus, and since a lot of people talk about the solving side of things, I'm going to talk a little bit more about the practicalities of the implementation side of things, how these things actually talk to your test benches and work in your various flows. So my particular journey through portable stimulus, right? Back in the 90s when I was in college at Princeton, I was doing undergrad work on AI, machine reasoning, which at the time was kind of real novel stuff, right? Then I joined industry. Around 94, I started using, basically, I was a new grad at AMD. They wanted me to write test cases. I didn't want to write test cases, so I said, hey, I can put this machine reasoning stuff to work, and started doing x86 test generation. And over a span of a couple of years, we quickly ended up with a very, very effective scheme for test generation. We started out in simulation, of course, but quick turn and emulation was a new thing then, right? Today it's become much bigger than it was then. So we applied it to quick turn, and then the program was big enough that we could afford to go build custom boards to run these same tests in actual silicon. And back in 93, 94, running 1 billion cycles a day was kind of a big deal. And we were finding 1 or 2 bugs a week on this stuff, right? So it was real early work before portable stimulus had ever been named. I started Brecker around 2003, largely because I kind of realized that this machine problem-solving approach to test generation, or this graph-based approach as we call it, was pretty effective. I wanted to bring it to more people. ST was one of the first people that we actually started portable stimulus with. What we'd done was we brought the graph-based technology to a fairly complex video controller they had, display controller they had, and they asked the question, hey, you have all this stuff running on, at the time, ERM, right? This is before we had VMM and UVM and OVM, ERM, but running on top of ERM, can you now please take the same knowledge and run it at the SoC C level? And that was kind of the start of our journey into portable stimulus. Then around 14, 15, Tom probably knows better, the Accelera portable stimulus working group started, and I didn't know anything about standards groups, but I sat in and said, hey, these guys really want to solve the problem that I've been working on for the last decade or so. And 3 years later, we just have a 1.0 release of the standard, and it has, I think, a lot of the nice randomization stuff. I think there's plenty of work left to be done in making this a full solution, and we're planning for a 2.0 release, I don't know, maybe in 2020 or something. Those plans are still a little bit up in the air. Why did I get into this problem? Okay, and maybe this slide talks to the audience more than any of the technology. Right. So Mentor does this nice research survey every couple of years, and there's very good data coming off of it. We've known for years that design is only about 30% of our cost, right? That 70% of our cost is in verification. We've heard that till we're a little bit blue in the face. When you dig into this information and sort of say, where is the time going? We find that a good 30% is in writing tests, right? So this assumes that you have your test benches and all your randomization, and you're using UVM and every other state-of-the-art we have in verification. We're still, in UVM, we're writing sequences. At the SOC simulation level, We are writing C tests. In post-silicon, we are writing diagnostics. We're spending a lot of time writing these tests. We got to write the tests. We got to write the checkers, right? The scoreboard. We got to write the coverage models. And this is a lot of work. And then the other big problem is we're spending a lot of time in debug. Well, what the heck does that have to do with test generation? So there, this doesn't come out in the Wilson survey, but I think if I speak to what we're doing in debug, if we say we're spending 25% of our time in debug, almost as much as we spend writing tests, we'll go, yeah, that's about right. That's what I do. Now let me ask you, how much of the time are you spending debugging bugs in your design? And that actually is the fun stuff, right? That's when what we're doing. That's when we do what we're being paid to do. But the bulk of that 25%, we're spending debugging that test that we wrote, because we hand wrote the test, we didn't quite get it right, and we missed a comma, or we missed an address, or whatever it is, and we spend a lot of that time debugging. So I got to thinking. So on test development, well, I got interested in how do we think about verification planning? How do we think about decomposing sophisticated scenarios into smaller pieces? And then how can we implement these scenarios in an abstracted fashion, which is a lot of what my presentation is about, such that tools can then deal with the scenario and map them to our various platforms. And then on the debug side, here was my experience, okay? So back in, whenever, 94, when we were doing all that x86 stuff, we built this beautiful constrained random graph-based test generator for x86, and it was a very, very successful project at the time. I had a team of 5 people building the graph. I had a team of 10 people debugging the tests coming off of that, because these tests were so complex, people couldn't figure out what was going on, and I needed an army of people just to sort out and triage and figure out what was going wrong, okay? That was no good, right? So that really got me to thinking about, well, we got to get past just the test generation to some form of high-level debug. If you're going to generate such sophisticated test cases, we really have to take that knowledge into the debug flow as well. And also, early on, right, I didn't want to write these test cases because I could only write, a test a day. But can we use test case synthesis? Can we take the analogy that we have for logic synthesis, where there's one RTL in, and based on which technology, manufacturing technology we are targeting, we'll generate completely different gates to match the technology we want to go to. Can we take a portable stimulus model as input, and can we synthesize the right test case for the right platform and make that all automated? Okay. And of course, we want all of this to be correct by construction. I mean, this is the beauty of synthesis. When's the last time you debugged? Stay still. I thought I was going to do ballet up here. So when's the last time you debugged a syntax error in a netlist? We just don't do this, right? Because tools synthesize these all for us. Why can't we do this with test cases? So these are the things that I really started to get interested in, really on how do people think, how are people reasoning about their verification problems, and what can I move into automation? Oops, that's not at all what I wanted. Boom. Boom, boom, excuse me. Okay. So all of that came together into a tool flow where we started thinking about, okay, we got to build these models. When I go into Verification Engineers Cube and look at, start talking verification, right? The first thing we do is we go up to a whiteboard and draw a little chart that says, well, to test my particular device, you got to do this followed by these two things in parallel, and then this thing, right? You know, 2 engineers can't talk without drawing 3 boxes on a whiteboard, right? So can we take those diagrams that people are creating on the whiteboard, and can we capture them directly into a visual construction tool? So that gave rise to what we've done to Track Designer, right? So this is a visual construction tool. I started to see lots of problems repeat themselves over and over in the industry, right? So one common one is lots of people are building ARM-based subsystems, and we test that the ARM cores and the fabrics and the memories and the coherency is all working correctly. So we built an app for that, right? We see lots of chips with very sophisticated power management schemes. and there's a repeating pattern on how you test power management. So we built an app for that. There's problems around security. This is a big thing in verification. And so we built an app for that. And these basically become VIPs for portable stimulus that you can plug into your model. And then that model goes into a synthesis engine, this TrekGen product, right? And he's the guy who does all the solving and generates the tests. Where a lot of the work at Brecker ended up being is actually at the bottom. So, in synthesis, we do the synthesis stage and then we do the optimization phase to actually map things onto a target process. In the same way, we synthesize a test case and then we optimize it for the platform. And maybe you're running in UVM, maybe you're running in SoC simulation, maybe you're running in post-silicon. And a lot of work is there in mapping these operations where we have common APIs that can run across all of these, and the tool is not simply generating the same tests, but generating different tests for each platform, fits to the platform. Why has this become an important problem? So the vision that I think Tom put out very nicely, we want one model that we can reuse, right? We want to be able to vertically reuse IP tests, subsystem tests, full chip. We want to be a horizontal reuse, simulation, emulation, FPGA prototypes, silicon. These teams, they are different people. They've come from different backgrounds. The environments work differently. And it's all very good to say, hey, as a corporation, each of us should go figure out how to get things working across each of these teams. And I know you're doing this. I mean, every company is trying to do this. And I know it's hard. And it's hard because people don't like to change. People have different constraints, different backgrounds, different views of the world. And if we can come along with the flow where the tool optimizes for each of these flows, then this whole debate goes away and the portability becomes much simpler, right? So there's almost a point of view that you can start focusing on even writing directed tests that are portable that are going across all of these flows. And my favorite thing to say about portable stimulus is that Brecker, we bring you your verification GPS. Okay. So if there's one thing you take away from my presentation, GPS. So I think these graph-based models, they're great for human beings. It's a great way to decompose. It's an algebra. It's a way of writing down how do you decompose these complex scenarios into the component parts so the tool can go figure out how to assemble it for you. It's portable, right? We can once we have the model written to this API, the tool kind of essentially looks like a synthesis engine with a bunch of dip switches, and we're simply setting the right dip switches for the right platform, making deployment very, very easy. Because you know that you haven't thought about all the deployment models you're going to want once you have this technology. And then to me, one of the biggest things is it's shareable. These graphs are very visual. People can look at them, argue about whether they're complete, argue about whether paths are legal, whether all the scenarios are there, what's been covered on this. So communication has been greatly enhanced. Okay, let's talk a little bit about the language itself, right? So portable stimulus provides us a way to actually define these graph-based models. Right. So over here I have some code and an implied graph from it, and a quick little tutorial, if you will. So we have actions A, B, and C. A produces some output, and B and C wants to consume that input, and they're all bound together. And in blue over here, you're seeing the data flow bindings over there. And then in action E, we have our entry point, if you will. We have some activity, and it says, I would like to schedule 2 occurrences of a select between B and C, right? And that gives us the purple portion, the control flow part of the graph, right? So this is how my tool interprets portable stimulus and turns it into a graph, okay? So the graph is all well and good, and then what does it look like when you're actually implementing these graphs, right? We draw these pictures, but we got to bring this down to sort of tie into your test bench. And what we're seeing people do is they'll build graphs, whether in the visual editor or in code or whatever it is. But then there's underlying code associated with each of these nodes, Okay, define the actions and the structure of the graph with PSS is pretty straightforward. And then within each operation, we're seeing people start to put in real code, right? So whether they're writing in C++ or the DSL, we a little bit don't care. But you'll recognize the UVM style register writing that those APIs being brought up to the PSS level. We're seeing them drive transactions, check registers. When they're trying to come along and predict what they're doing, well, the prediction of what is happening is very much a function of what path through the graph they took. So we're seeing them put procedural code into these models. And the nicety over here is that way everything is moved up to the PSS level, and we can use the synthesis engine to go generate a test case for a particular platform. So what does that mean? Oops, I did that again. Excuse me. Okay, now I got to find the slide. Okay, I'm on the slide. For those who are far away, I have a remote over here, and it has an escape button that I keep hitting instead of forward. Okay, so let's say we had a little SoC, or we're testing just one function of an SoC where we have some CPU, some memory, some fabric, and a little UART. We might have some model that thinks about what are the different ways of configuring a UART. And the example is trivial, but it's useful as a user to wrap your mind around it in terms of the kinds of things you can do with graph-based configuration, right? So in a UART, you make a decision whether you have a parity on or off, and only if a parity is on does it matter whether your parity is even or odd. Now these are 2 bits, and you could do this with a constrained random thing in your sleep, but your real-life problems are much more complex, and they're of this nature, and being able to draw these graphs of all the different config paths is important. And then when the tool is running, right, maybe once you've picked your configuration for parity, we got to write that into the UART. So maybe that's something that is either code for a CPU or transactions for a VIP. But then we need to configure the VIP to match, to have the same parity rules, otherwise the communication won't work. Then maybe on the software side, we are sending data. And then maybe on the VIP side, we've got to check data. So the point is when you're really discussing portable stimulus, your chips have to have inputs and outputs. They have to communicate with the rest of the world, right? If you don't talk to the outside world, we ain't doing squat, right? So we need our portable stimulus models to be able to not only read and write registers, read and write memory, but they also got to be able to drive transactions. And this is easy when we're in a UVM world to do. A little bit more complex in a software-driven world, even more complex when you're going up to emulation, in-circuit emulation, and post-silicon flows, okay? And all of these are the things we've been working on automating. Okay. So once we have these models from the PSS model, Trek SoC can either go to an SoC simulation, you can go to a UVM environment, you can go to a post-silicon flow. Coming back to the synthesis idea, at that point, which test bench you're running on becomes a detail, right? And a lot of technology there, a lot of figuring out how to create flexible flows that'll fit with how the post-silicon guys work, fit with how UVM works, fit with how the SOC simulation works, and all of the limitations we have in each of these platforms, right? Okay. The tool itself, remember, it came out of machine reasoning. So it really wants to think about the graphs and reason that paths to the graphs. So once we have a model, it's thinking about this graph. And when you look at the number of paths that are implied by a graph, they're astronomical, right? Having a graph with, what do I have over here? 10 to the 67 paths. I mean, it's just nothing. And the fact is, you guys know this, right? If I asked you how many possible tests are there for your SoC, it'll kind of blow your mind to think about the question, but if you really started to think about it, you're going to come up with a number like this. And you kind of know that you can't run them all. You kind of know that you don't really want to write a coverage model that wants them all because you're not going to satisfy it. And we kind of start writing a coverage models to be something that we can actually satisfy. But if you have a tool that's reasoning about these spaces, reasoning about what paths through the spaces can be constrained, what paths through the spaces can be reached, it's reasoning about, let me start with what are the checks I want to create and figure out how to create stimulus for those checks. What it's doing is automatically, even before you're given any information, leading with the most important tests, right? You want to make sure that you've done at least one of every kind of check coming out of your model. You can do static analysis on these models. There are graphs and there are constraints, paths you can reach, paths you can't reach. So it'll tell you, hey, here's a node you can't reach. That's kind of a little darker red than somewhat slightly lighter red over here, where the tool is trying to tell you, hey, some paths to this node are okay, but there's certain paths that you have constrained out. Is that okay with you, right? So this ability to start thinking about, here are the constraints on my search space, here's what I can do, here's what I can't do. Effectively, this is the best case coverage I'll get out of my model. Is this what I mean? Is this the search space I'm after right now? Or more interestingly, we have a bug, we're putting in a constraint to work around the bug, and half this graph has gone red and go, okay, that constraint interacted with something that we didn't meet, right? So this ability to understand your reachability before you go into the flow is important. Okay, so that tells us what we're going to run. Then we start generating tests. And I talked about high-level debug, right? So one of the things that Brecker innovated was this notion of high-level debug that's common to UVM SOC simulation post-silicon, where we are thinking about the schedules, where in this case we have 4 CPUs, 1 thread per CPU. The picture kind of updates as the test is running. The green nodes are done. The yellow nodes are started but not finished. Blue nodes are waiting to run. Red node is a failure because all these tests are self-checking. Some vision of how is memory being used, right? And how is memory being allocated. For each action, you can ask, hey, what data locations were used by this action? And it'll show you not only the addresses, but what data should be in memory before the action ran, and what should be in memory after the action ran. And this is all at generation time before we even run the test. So you can imagine this is invaluable when you're debugging and trying to figure out what's going on. And you're not having to look, trying to debug system tests, these complex tests at the wave level, right? We have great debuggers at the wave level, but we got to move up a level, think at a higher level of what was the scenario, how did the operations relate? If this scenario failed, who was the guy who was my producer? I don't want to go search 1,000 operations, right? Okay. Oh, and deep integration into Verdi, right? Verdi provides a very nice open API for allowing other tools to integrate into it. So once you're debugging over here and you're ready to go down into signal level, you can go into Verdi, start screwing around in the waveform, go, oh, my error was 2,000 cycles ago. You move the Verdi cursor, and our time cursor will move back to show you what's going on at the high level at that point in time. Okay. And then, so I talked about how we first look and control what we're going to generate. Then I talked about when the tests are run, how do you debug them. Now let's talk about coverage and coverage closure. So the problem solver, right, the machine problem solver, he is looking at the entire search graph. And we can run in random mode and we'll probably get our 80, 90% coverage. In fact, even running on random mode, it tends to get very good coverage because it's starting with, have I tried all of the checks, right? So you'll be happy with what it's doing. But we really want to know that we've got 100% coverage. We don't want 95% coverage. So you can put it into coverage closure mode. And then finally, you can export the coverage to your Sentinel coverage tools. So there we are in summary. So portable stimulus, a powerful way to define your verification intent at the abstract level. And a lot of the work that Brecker has done with Trek SOC is take these models and do the optimization phase, map them onto each of your platforms so you don't have to have these big debates across teams as to what is the best way to do it. And it's a great way to analyze and think about what test cases you need to hit and look at what coverage you've achieved. Thank you very much.
Thank you, Adnan. Do we have any questions from Bristol? No questions from Bristol. If we can quickly go to Cambridge. Hi, Chris. Do you have any questions?
No questions from Cambridge this time.
Thank you very much. Well, we have no questions from Grenoble, so it's just to leave us to say thank you very much, Adnan. Really appreciate your presentation. Thank you.